Continue from our 10.9 last time. We will continue with the second part of this section, which, as I remember, this section was separated in the previous edition of this textbook. Now, basically, it says the following. Suppose our fx is representable by a power series. Then the first derivative can be represented by the term-by-term derivative of that series. You see, when you do the first derivative of this, right? So the derivative of c and the coefficient of the nth term times x minus a to the n. When we do the derivative here, notice that the constant, the coefficient will stay the same, right? Okay, and then this n move to the front. X minus a to the n minus 1. Okay, now the thing is, we don't start from 0 anymore, we will start from 1. The reason is the first term here is a constant. The first term here is a constant. You see? So when we do the derivative, that constant will become a 0. Okay, the 0th term, I should say. Okay, let's write it down so that you can have the intuition. Suppose we have that fx equals to the sum from n equals to 0 to infinity of cn x minus a to the n, which we can write as c0 plus c1 x minus a plus c2 x minus a squared all the way to cn x minus a to the n, and even further on. Then the derivative, derivative of that function will be, this guy will become 0. This guy will become just c1. This guy here becomes c2 times 2 x minus a, all the way to cn times n x minus a to the n minus 1. Right? So you see from here that the first term is c1. So let me start from n equals to 1 to infinity. Okay, that's cn times n times x minus a to the n minus 1. Right? This is the general term here. Okay. Now, the thing that you need to pay attention is that when you do the derivative or integral of that power series, the power series representation, then you will keep the same radius of convergence. The radius of convergence will be the same. Now, even though the radius of convergence will be the same, the interval of convergence may differ at the endpoints. Okay, so suppose, for example, the original radius of convergence is a minus r, a plus r, for example. Okay, that's the interval of convergence. Now, when you do the derivative, then it is possible, the radius convergence is still the same, the center will still be the same, okay? But it may differ here. It may becomes closed interval on one side or both sides. Likewise, when you integrate them, okay? Likewise, when you integrate, it is possible the endpoints, it is possible that the endpoints change becomes a closed or becomes an open interval. Okay, but the radius of convergence will be the same. The center will be the same. Basically, that everything inside here will be the same. Okay, it's just different at the endpoints. Okay, now as for the integral, when we integrate that series, we integrate that term by term again. But what happened is, of course, this guy becomes this, right? Okay, but when you integrate a function, you have extra constant, don't forget, right? You have extra constant, and we can find that constant another method, by using another method. We need to find that constant though. Okay, we need to find that constant later on, but we can find it another way. Or maybe we just leave it as a constant. Just don't forget, when you integrate indefinite integral, you need to have plus constant. Okay, now our textbook actually give us some nice examples, and they are so nice that I want to go over them. The first one, the first examples is the power series representation for 1 minus x squared. Now notice that this is the derivative of 1 over 1 minus x. Okay, that's the derivative of 1 over 1 minus x. Therefore, this is the derivative of the power series representation also. From n equals to 0 to infinity, which is equals to the summation of the derivative of x to the n respect to x, from n equals to 0 to infinity. Okay, that's n times x to the n minus 1, supposedly from 0, but the constant part disappear, right? So I will start from 1 now, and you can see that it has to start from 1. Otherwise, if you start from 0, then you have x to the negative 1, right? Okay, and up to infinity. Another one is natural log of 1 plus x. Natural log of 1 plus x is the integral of 1 over 1 plus x dx. That is equal to the integral of the power series x to the n from 0 to infinity dx, which is equal to the summation of the integral of x to the n dx. The one I want you to pay attention is this though. The derivative of summation, I should use different color. The derivative of the summation equals to the summation of derivative. You see how it changed? Okay. The integral of summation equals to the summation of integral. Okay, you see that? Because derivative and integrals are, we call that linear operator, which means the derivative of the sum of two functions, the derivative of the sum of two functions equals to the sum of the derivative. That's what they call linear in that kind of sense. Okay, the summation, the derivative of sum equals to the sum of derivative, right? The integral of sum equals to the sum of integrals. Now, so using that idea, then we can interchange the integral and summation, the derivative and summation. Okay, now then here I will get, of course, this is still from 0 to infinity, right? Okay, and the integral will be 1 over n plus 1. Oh, sorry, I forgot the summation notation. From 0 to infinity of x to the n plus 1 plus a constant. Okay, don't forget this, plus a constant. Now, how do I find that constant? To find that constant, you choose an x. Usually we choose a nice x. For example, for x equals to 0, I will get ln1 equals to the summation of 1 over n plus 1 of 0 to the x plus to the n plus 1 plus constant. Now, what is ln1?
Zero.
ln1 is 0. Okay, but the summation of zeros is also 0, which implies c is a 0. Now, from there, then we say, so this ln 1 plus x is representable by that series from 0 to infinity of 1 over n plus 1 x to the n plus 1. Which, if you think about it, by the way, pay attention here. If you think about it, I can also rewrite it this way. I will change my counter, my index, starting from 1. If I start from 1, what will happen to 1 over n plus 1? It becomes 1 over k, and this is x to the k. Is it okay? That's the play of indexing. Because when n equals to 0, this is 1, this is 1. When n equals 2, this is 2. If this is n equals 1, this is 2, this is 2. So always one more, right? But I start from 0. Let's say if I start from 0, my series start from 1. Let me just start from 1 right away, right? Because this will be the same anyway. Okay? If you kind of like confused, are they the same or not? Try to write the first few terms. Try to write the first few terms to see. Okay, so like this one here, if I write the first few terms, there'll be 1 over 1 x to the 1 plus 1 over 2 x to the 2 plus 1 over 3 x to the third, and so on, right? While the one on the right-hand side, I start from 1, not from 0. 1 over 1 x to the 1 plus 1 over 2 x to the 2, 1 over 3 x to the third, and on. Okay, now many times, however, when you do problems in our textbook, when you check and you check against the solution at the back, you see something different, and that's usually, if you do everything right but you see something different, it's usually because of the indexing. Okay, so they play with the indexing later. Okay, now furthermore, this is example 2, huh? Okay, example 3. What is the power series representation for this? This is the series of negative x to the negative x squared to the n, right? Which I can simplify to be, negative 1 to the n x to the 2n. Is it right? Yeah, it looks like this. It looks like 1 minus x squared plus x to the 4 minus x to the 6 plus x to the 8 and on. The thing is then, notice that tangent inverse x is actually the integral of this 1 over 1 plus x squared dx. Right? So which means that can be represented by integral of the summation from 0 to infinity of negative 1 to the n x to the 2n dx, which is equals to the summation of integral negative 1 to the n x to the 2n dx. Which will be negative 1 to the n stays the same, x to the 2n plus 1 over 2n plus 1. But because I start with because I integrate, don't forget I need to have plus c. Okay, now then to find c, I let my tangent inverse 0, which is known to be 0, equals to the summation of 0 over 2n plus 1 plus c. So from there we find out that c equals to 0 again. It's not always true though. It's not always true. Okay, so you have to check this. Okay, so in conclusion, tangent inverse x is representable by the series negative 1 to n x to the 2n plus 1 over 2n plus 1. Okay. Now, don't forget, we did start from the fact that the radius of convergence for this is 1, right? The radius of convergence, you see that what happened here is absolute of negative x squared has to be less than 1. And that implies x, absolute of x has to be less than 1. Right? Therefore, the radius of convergence is 1. Now, according to our theory earlier, the radius of convergence here will still be 1. Okay? The radius of convergence will still be 1. You can use ratio tests actually to check the radius of convergence here. Okay? But you will find that's actually still 1. Okay? If you want to check that radius of convergence. I will not do that anymore. You can do it yourself. why we learn this? Why do we want to learn this? Because of the following. We will do some problems later on. Okay, we will do some problems later on. But sometimes you end up with some function that is not integrable and not integrable analytically. So we settle with numerical integration. Now, what we mean by numerical integration, this is one of the methods. Okay, our textbook has this example. Our textbook has this example. Example, integral from 0.0 to 0.5 of 1 over 1 plus x to the 7 dx. Now, trust me, this is not integrable as usual. Okay, now, but notice that we can represent this by a power series, and the radius of the convergence is 1, which means it is well represented in this interval. Okay, let's work it out. Let's work it out. But I will slow down a little bit now. So solution. Okay, now this 1 over 1 plus x to the 7 is representable by n equals to the series from n equals to 0 to infinity of negative x to the 7 to the n, which is, you see that it is alternating series, is it right? X to the 7n. Okay, such that the integral of this function here is representable with, oh, of course, I need to say that the radius of function is what? Well, negative x to the 7 has to be less than 1, right? Then when you solve that, absolute of negative is absolute of positive. You do the 7th root of 1, that's still 1. So the radius of convergence still 1. In other words, we can represent this function on interval at least between negative 1 to 1, not including the endpoints. Okay. So as long as your integral is done in this interval, you can use this power series representation. Okay, now let's see what happened to the series first when we integrate that. This is the sum from 0 to infinity of the integral of negative 1 to the n x to the 7n dx, which will be the sum from 0 to infinity negative 1 to the n x to the 7n plus 1 over 7n plus 1 plus constant, right? You will see, because we have definite integral, then I don't need to find that c. You can find it though. Actually, if you want, you can find it, but no need. Because then, if I integrate from 0 to 0.5 of this, this can be expressed by the summation from n equals 0 to infinity negative 1 x to the 7n plus 1 over 7n plus 1 from 0 to 0.5. Now, I want you to be aware that this interval is a sub-interval of interval of convergence. Is part of this. Okay, without this, we cannot go on. Now let me plug that in. So we have this is equal to the summation on, so this is negative 1 here. So negative 1 to the n, 0.5 to the 7n plus 1 over 7n plus 1. Now you tell me then, how many decimal places you want this to be accurate? Let's say what we want to be accurate to, let's say 10 decimal places. Okay, in other words, the error is less than 1 times 10 to the negative 10. Okay, let's say that's what we want. So notice that this series is alternating series. That series is alternating series. So the error of this series, okay, will be less than, the error of this series will be less than the nth term. Will be less than the nth term. Now we want this to be true. Okay. Now let's find what term. Find the term we know that the E, the error will be less than the nth term. Okay, so I will set this nth term to be less than 1 times 10 to the negative 10. Okay, find the term n such that a sub n is less than 1 times 10 to the negative 10. Okay, so the magnitude, actually, I just need the magnitude. Okay, so 0.57n plus 1 over 7n plus 1. Find that n. Find that n. Oh, hold on. So this is 1 over, that 0.5 happens to be 1/2, right? Is it okay? So this is 7n plus 1 times 2 to the 7n plus 1. Is it right? This has to be less than 10 to the negative 10. Let me continue here. So if I do the reciprocal, then 10 to the 10 will be less than 7n plus 1, 2 to the 7n plus 1. Okay, and then you do try and error. Okay, you do try and error. What is the n such that it is true? Let's see. When n equals to 3, that will be This guy will be 7 times 3 plus 1 times 2 to the 22. That's 22 times 2 to the 22. Is it true that it's less than 10 to the 10 is less than that? Let me use my calculator. Give me a second. Okay, so 22 times 2 to the 22. Is it to the 10 already? 1, 2, 3, 4, 5, 6, 7, 8. Not enough. Not enough. So let's try 3. Go back here. That's no. That's not true. Let's try when n equals to 4. When n equals to 4, I get 7 times 4 plus 1 times 2 to the 29. Basically, I need to see if 29 times 2 to the 29, is it greater than 10 to the 10? Okay, go back to our calculator. So 29 times 2 to the 49. Woo! It's more than 10 to the... This is how I see it. This is 10 to the 10. And this is more already. Okay? So, yes, we get it. So, we get it. That's true. Yes. Okay? This implies the fourth term is already less than, the magnitude of the fourth term is already less than 10 to the negative 10, right? So we need just 3 terms, not 4 terms. Remember alternating series test, alternating series, the remainder of this series is less than the series that you start truncating it. Okay, so if you truncate it at 4, okay, so you just need to add up to 3. That's for alternating series test. So basically the integral from 0 to 0.5 of 1 over 1 plus x to the 7 dx can be approximated by this series, but up to 3 terms. Can be approximated by that series from n equals 0 up to the third term of -1 to the n 0.5 to the 7n plus 1 over 7n plus 1. Okay, which is equal to, when n equals to 0, that's 0.5 over 1 plus, when n equals to 1, it becomes minus 0.5 to the 8 over 8. That's when n equals to 1, right? Plus 0.5 to the 15 over 15 plus 0.5 to the 22nd over 22nd. This is accurate to and decimal places. And from here, you can use your calculator.
Will that last one be minus?
Yes, you're right. It should be minus. Because it's alternating now. I basically, if you take a look, I basically go over the examples in our textbook. Now, if possible, you take a look at this question here, this question. A big question. What is E? I'm sorry, pi. What is pi? Now, we know that pi is approximately 3.141 something, or 3.142 basically, right? But you have heard that there is some people, they want to find pi accurate to how many decimal places? Many decimal places, okay? In other words, we don't actually know the value of pi, right? But if we want to find, let's say, accurate to 20 decimal places, how do we do that? How do we do that? If you take a look at the side note of our textbook, they actually get it from here. They actually get it from here. They actually get it from here. They actually get it from there. Okay? They actually get it from there. In fact, what happened? What did I do? I'm not deleting anything. I want to grab, where's that? I want to grab this one here. Let me grab this one. Copy that here. Copy. Put it here. Now, what is the actual value of pi? Notice that tangent inverse 1 is known to be pi over 4, right? But at the same time, on the right-hand side here, when you replace x by 1, you basically replace this x by 1. Okay, so we then get when n equals to 0 and x equals to 1, you get 1. And then minus 1/3 plus 1/5, right? Because x is equals to 1. Maybe I write the series first instead of jump right away there. Yeah, because x equals to 1, right? That's 1 to the 2n plus 1. But this guy is, let me just ignore this for now. But if I expand that series, I will see 1 minus 1/3 plus 1/5 minus 1,7 plus 1,9 and on. That's infinite series. Alternating series, right? Okay, such that then if you want to know the actual value of pi, multiply that by 4. You see what I mean? So if you want to compute, you know what, I want to know uh, the value of pi up to, let's say, just for simplicity, I want to accurate to 10 decimal places. Okay, then my nth term has to be less than 10 to the negative 10. Do the reciprocal both sides. Okay, so 2n plus 1 should be greater than 10 to the 10. Okay, so how many terms do I need to add to get that kind of accuracy up to 10 decimal places? Then I need to have a lot of terms to add. Many terms. Can you imagine that? Right? 10 to the 10 is 1. That's 10 to the 10. Subtract by 1 divided by 2. So 9,999,999,999 divided by 2. And this n has to be integers. So we can say n at least has to be greater equals to, because n has to be integers, it has to be more than 5 billion. You need to add 5 billion terms to be accurate to 10 decimal places. Okay, now that's a lot, I know. But that tells you why it's so difficult to approximate that pi. Okay, this is one way to approach that. There must be another way to approach it, another better way to approach that. Okay, yeah, another better way to approach that. Let's say if you use, for example, I think this one would be a lot faster. Tangent inverse of 1 over radical 3, for example. We know this is equals to pi over 6, right? But then the series actually converge a lot faster. That will be negative 1 to the n here, to the n, and then it will be 1 over radical 3 to the 2n plus 1 over 2n plus 1. So pi over 6 is equal to, let me simplify this a little bit, that's negative 1 to the n over 2n plus 1, and then that's 3 to the n square root of 3. Okay, then so pi will be 6 times the following series. When n equals to 0, I will be, let me take the radical 3 out. So when n equals to 0, there will be 1 minus. When n equals to 1, that will be 3 and then 3 here. When n equals to 2, there will be 5 and 3 squared here, minus 7 and 3 cubed here, and on. So you see that this guy here, the n term actually goes to 0 a lot faster. Okay, it goes to 0 a lot faster. So if we want to make it accurate to 10 to the negative 10 decimal places, then I need to have my 1 over 2n plus 1 to the 3n to be less than 10 to the negative 10. In other words, my 10 to the 10 should be less than 2n plus 1 to the 3n. Then I go back to my calculator. I go back to my calculator. 2n plus 1. Let's say, what's that mean? 2n plus 1, 3 to the n. 3 to the n. So are we at our calculator now? Okay. So let's say n equals to 4. When n equals to 4, that would be 9 times 3 to the 4. No, this is way too small. This is way too small. 20. Maybe 20, up to 20. Maybe 20. Let me try 20. So if 20, so that will be 41 times 3 to the 20. Oh, yeah, you see? Okay, we just need to add 20 terms. Ooh, you see? A lot more effective, huh? Nice. So I get when n equals to 20, then this is true. So I just need to basically then, I just need to add 20 terms of this to make it accurate to 10 decimal places. Okay, now I don't want to go too much into that, but I hope you can start feeling it. Okay, now let's see number. Let's see number 14. I'm doing problems now. Number 14. Number 14. Find the power series representation of fx equals to ln 1 minus x. And use equation 1. Where's equation 1? Oh, scalar. Okay. So we know that 1 over 1 minus x has this power series representation. So what is the integral of this? The integral of 1 over 1 minus x dx will be negative of ln 1 minus x. Is it right? Yeah, try to integrate that. You do substitution, you get negative, right? Okay. But this is equal to the integral of the power series. So negative natural log of 1 minus x. Therefore, what makes this section difficult today is the fact that you need to be creative enough to find out how to get this. Okay, if you don't know how to get this, nothing can be done. You have to be creative enough, like what do you do to this 1 over 1 minus x such that you can get that thing. Okay, now fast forward, if I integrate this, I will get the summation of x to the n plus 1 over n plus 1, start from 0, supposed to be plus constant, but when my x is 0, you will see my c equals to 0. Okay, so basically, if I update that, I will get negative ln of 1 minus x is equal to the series and equals to 0 to infinity of x to the n plus 1 over n plus 1. Now I will move the negative. So natural log of 1 minus x will be negative of that power series. Okay, that's for part A. That's the question for part A. Now, and then part B. Part B, find the power series representation. Find the power series representation for another function fx equals to x ln 1 minus x. Well, we just multiply x in. Right? Furthermore, this will be negative summation from 0 to infinity of x to the n plus 2 over n plus 1. Then part C. Then what is f1 half? What is f1 half? I guess the question is, I'm sorry, the question is more about what is ln 1 half. Now ln 1 half is natural log of 1 minus 1 half, right? Basically, I replace the x by 1 half. So I will use this series here. Let me use this color. I will use this series here. So that will be equal to negative the series 1 half to the n plus 1 over n plus 1, which is it's 1 over n plus 1 to the power times 2 to the power of n plus 1. Okay, now, and the question is express ln2. Express ln2 as the power series. Now ln2 is negative of ln 1 half, is it right? Which is equals to the negative of that negative, the negative of is negative. The negative cancels. When n equals to 0, that's 1/2. Plus, when n equals to 1, that's 1 over 2. I think I will write it this way. 1 times that 2 times 2 squared plus 1 over 3 times 2 to the power of 3 plus 1 over 4 times 2 to the power of 4. And so on and so forth. Okay. How about the radius of convergence? The radius of convergence in this case will stay the same from our original geometric series. Okay, because we developed that from here, then the radius of convergence for that series is still from 0 to it's still 1. Notice that I use my x 1/2. Okay, this 1/2 is in the interval of convergence. But then using that 1/2, I find out ln2. Okay. Let's take more examples. See, I spent basically 1 hour just for the second part of this 11.9. Okay, let's see, for example, number 16. Number 16, we have fx equals to x squared times tangent inverse of x cubed. What is the power series representation? Solution. Do you remember what is the power series representation for tangent inverse x? If you don't memorize it, then you have to develop that yourself. Or cheat from the book, or cheat from the note, right? Okay, but I remember that's the integral of this guy. Is it right? So it must be the integral of this series here, that's -1 to the n, and then x to the 2n over x to the 2n dx, such that the integral is -1 to the n x to the 2n plus 1 over 2n plus 1, that series. So that's an alternating series. Infinity n equals to 1, -1 to the n x to the 2n plus 1 over 2n plus 1. Plus constant supposedly, okay, but we find out the constant was 0, so I will just ignore it. Because when x equals to 0, tangent inverse 0 is 0. Okay, now then from there, what happened if I replace my x by x cubed? If I replace my x by x cubed, then tangent inverse x cubed will become the series from -1 to the n. I will replace this x by x cubed. Okay, which is equal to the series from, I'm sorry, it should be from 0, not from 1. It should be from 0 here. It should be from 0 here. So 1 to the n times x to the 6n plus 3 over 2n plus 1. That's tangent inverse of x cubed. So then what will x squared tangent inverse of x cubed be? Multiply the whole series by x squared. X to the 6n plus 3 over 2n plus 1. Finally, we get the series from 0 to infinity, negative 1 to the n, x to the 6n plus 5 over 2n plus 1. That's the power series representation that we developed from the geometric series. So the radius of convergence is still 1. That's a lot, huh? I'm sorry, that's the easy one. How about the harder one? Honestly, I look at this question, I don't know the answer. Number 18. I can't even imagine how I want to approach this. This is x over 2 minus x to the power of 3. But at least I know this is x cubed times 1 over 2 minus x to the power of 3. Let me factor 2 cubed at the bottom. So I will go further. See, sometimes you look at the problem, you don't know what to do until you start writing it. So the key is write it down properly, please. 1 over, this becomes 1 over x over 2 cubed. Okay? Now, so if I can find the power series for this, if I can find the power series for that, that would be so nice, huh? Don't you think so? If I can find the power series for that. Okay, then let's start. Let's start with, I know 1 over x, 1 over x, 1 minus x is the series of x to the n. So the derivative will be 1 over 1 minus x squared. That will give me n times x to the n minus 1. Earlier start from 0. Now because I do the derivative, I start from 1. But this is actually the same to negative of 1 minus x to the negative 2. Let me do the derivative once more. The derivative once more will give me 2, this is 2, 1 minus x to the negative 3, right? I think I should say negative of negative 2. So this is 2 over 1 minus x cubed. Okay, so that's the derivative. And you do another derivative. So the series now start from 2, and this is n times n minus 1, x to the n minus 2. Okay. Now I plug this in. I get here. Shoot. Okay. So one. Oh, actually, not yet. Huh? Okay. I need the x to be. I need the x here to be x over 2, and I need this to be 1. Let me modify that first. So, so erase. So 1 over 1 minus x over 3q, I divide by over 2, not over 3, over 2q. I will divide the whole equation by 2, and replace x by x over 2. Okay, or n times n minus 1 times x to the n minus 2 over 2 to the power of n minus 1, because I multiply the 1/2 in. Hey, we are very, very close already. Almost there. Be patient. What do I need? I need, so x cubed over 2 cubed times 1 over 1 minus x over 2 cubed is representable by x cubed over 2 cubed series n times n minus 1 x to the n minus 2 over 2 to the n minus 1. So x cubed, I'm sorry. So finally, x over 2 minus x squared, cube, is now equal to the series from 2 to infinity of n times n minus 1. I multiply the x cubed in, it becomes x to the n plus 1 over, I multiply the 2 cubed in, I get 2 to the n plus 2. That's the power function representation. Now, how about the radius of convergence? Notice that I actually have it here. I actually have it there. Notice that I replace x by x over 2. Okay, so the original radius of convergence supposed to be 1, and I replace that x by x over 2. So my radius of convergence now becomes 2. Okay, now it's 5:41. I want to give myself a little break. I would like you to try number 20. I would like you to try number 20, whose function is x squared plus x over 1 minus x cubed. Now, notice that we already have that. We already have this guy here. So 2 over 1 minus x cubed, we already know That's the series n times n minus 1 x to the n minus 2 for n 0 to n from 2, not from 0 to infinity. Okay, so this guy here, the 1 over that, you can have the 1/2 already. You see? Okay, so basically you multiply by x squared plus x to get that series. That should take you like around only 3 minutes though. Okay, together with the break, we come back at, let's come back at 6 o'clock. So if I multiply that in, I will get 1/2 the series from 2 to infinity of n times n minus 1 times x to the n plus x to the n minus 1. Actually, let me just write it this way first. That would be x times x plus 1, that's what I multiply in, x to the n minus 2 over, nothing over, no over. And this will be 1/2 series n minus 1 x plus 1 x to the n minus 1. I think that's good enough. Okay, that's for number 20. Let's go on. Suppose I want to do number 28. So number 28, evaluate the indefinite integral as a power series. Integral of tangent inverse x over x dx. Give me a second. My son wants to play with me. Let's come back. What will happen then? I will represent this first. Okay. Do you remember what is the representation for tangent inverse? I remember that's from this guy. So this will be the series -1 to the n x to the 2n. And from 0 to infinity, the integral of that will give us the tangent inverse x. So if you memorize that, that would be a lot better though. Okay. So this will be the alternating series x to the 2n plus 1 over x, over 2n plus 1. Over 2n plus 1. So, if I have tangent inverse x over x, that will be the series divided by n. I divide by x, right? So it becomes x to the 2n only. okay, divided by x. Therefore, the integral of tangent inverse x over x ex is the integral of that series n equals to 0 to infinity. Actually, I need to be careful that it's supposed to be plus c here, but we found out that the c was 0, right? I hope you remember that. But don't forget the c. Make sure you deal with that. And then this will be the series from n equals 0 to infinity of -1 to the n, still the same, x to the 2n plus 1 over 2n plus 1 squared. Of course, plus constant. Okay, we are done with the power series representation of that. That's for number 28. How about number 32? Number 32, integral from 0 to 0.3 of x squared over 1 plus x to the 4th dx. Now, this integration is not doable by power series, by analytically. We cannot. But let's see how can we deal with this. We know 1 over 1 plus x is alternating series, -1 to the n, x to the n. Now replace that x by x to the 4th.
I thought it was -1 minus x. 1 over 1 minus x.
Yeah, if you use minus here, then you don't have alternating.
Oh, okay, right.
Right? Now then I will replace that x by x to the 4th. So I get -1 to the n, x to the 4n. So, right? Now then, if I multiply by x squared, that's x to the 4n plus 2. So when I integrate that from 0 to 0.3, which is well inside the radius of convergence, that will be the integral from 0 to 0.3 of that series. Oops, I missed the alternator. And that will be the series from 0 to infinity of -1 to the n, x to the 4n plus 3 over 4n plus 3 from 0 to 0.3. When x equals 0, the series is 0, so this series is this is 0.3 to the power of 4n plus 3 over 4n plus 3. Okay, so that's the power series to represent that the value of that integral. Now, the thing is, they have follow-up question. The accurate tool 6 decimal places. Basically, in other words, the error should be less than 10 to the negative 6. Now notice that this series is alternating. This series is alternating. Okay, so we need to find n such that the nth term is less than the allowed error. Okay, with absolute sign. So we need to look for that n, 0.3 to the power of 4n plus 3 over 4n plus 3. We want this to be less than 10 to the negative 6. Or in other words, 10 to the 6 is less than the reciprocal of that, 4n plus 3 over 0.3 to the 4n plus 3. Then from here we do trial and error. Get my calculator again. Let's use n equals to 4. Can I use 4? Is it reasonable to use 4? I'm just guessing. I'm just guessing. Okay, when n equals to 4, what happened? Is it true that this will be 1619 over 0.3 to the 19? Okay. So maybe I would say this is actually the same to say 4n plus 3 times 0.3 to the negative 4n minus 3. Negative exponent. Well, anyway, I use my calculator. So 19 divided by 0.3 to the power of 19. Oh, it's so big. No, it's way too big. I don't want it. Go back. Go back. It's way too big. What do I get there? 1.6 e to the 11. So that's way too accurate. And somebody say, no, I don't want to be that accurate. So this is 1.6 blah, blah, blah times 10 to the 11. Oh, let's try n equals 3. Is it true that 3, so that's 15 over 0.3 to the 15? Over 0.3 to the power of, oops, sorry, wrong one, to the power of 15. Is it 10? 1, 2. It's definitely more than 10, huh? It's definitely more than 6 decimal places. Okay, let me go back. Let's equal it. Oh wow, it seems like it converged quite fast. So this is 1 something 10 to n. Let's say n equals to 2. Let's say n equals to 2. So is 10 to the 6 is less than 2, so that will be 11 over 0.3 to the 11. 11 over 0.3 to the 11. This is more than to the power of 6 already. Okay, it's more than to the power of 6 already. 6 times 10 to the 6. So this is 6 something times 10 to the 6. So we just need to truncate it at a sub 2 is already less than 10 to the negative 6. So we need up to one term before that. Ooh. So we just need the first term. So what is the first term again? The first term will be, oh, 0, 1. So the summation, this integral here from 0 to 0.3 of x squared over 1 plus x to the 4 dx. That's equals to the series from n equals 0 to infinity, negative 1 to the n, 0.3 to the 4n plus 1, 3 over 4 and 3. And we just need to approximate that using from 0 up to 1. Wow, do you think this is really nice? Just using two terms, the 0 term and the first term, we are accurate to 6 decimal places already. So this is when n equals to 0, I get 0.3 cubed over 3 minus 0.3 to the 7 over 7. Let's see. Using my calculator, 0.3 cubed over 3 minus 0.3 to the 7 divided by 7. So I get 0.08969. So this integral is approximately 0.008969. This is 6 decimal places. Okay. Now your suggested homework from here, will be from number 3. I think I already assigned you from number 3, but I would like you to go all the way to number 31. 11.9b up to number 31. Skip the one requires you to graph. So skip number 21 and 23. You don't need to do those. Now, let me go on to 11.10. Our course will end at 11.10, not 11.11. Okay, only at 11.10. I don't want to go further than that. And this 11.10 is another long section though. Okay, so let me call that 11.10a. I'm actually starting to have fun with this though. Why? Because we can get very creative. Now, what is this 11.10? Taylor and Maclaurin series. Taylor and Maclaurin series. Here's the thing. We in 11.9, we developed power series representation from the power series representation of 1/1 minus x, which is this guy. Okay, so we start with a power series, and from there we go on. So we already have power series representation and develop another power series representation. Okay, that's what we did in 11.9. Now in 11.10, we will attack a more general situation. Okay, suppose we have a function. Suppose fx is given. How do we find its power series representation? Its power series representation. If any. Okay, now so for the next 10 minutes, maybe up to 15 minutes, I will derive the pattern. It's actually in the book. It's actually in the book. But our textbook tried to explain it in too much details. I mean, a lot of details. That's very nice. But the way they structure it make you not able to see it. Okay, I will try to make you see it. So here's how I will do it. Here's how I will do it. Suppose, so let fx be representable by this power series Cn x minus a to the n and 0 to infinity. With x minus a, the interval of convergence, to be R. So we start from a function that we assume to be representable. Okay. Now, what we will do first is we need to find, how do we find this Cn? So there are two questions. There are two questions we will need to answer. The first one, we will need to find the coefficients. And second, is this the power series representation? Well, we assume that first time, right? We assume it first. But with that assumption, we need to check later on if this is a good representation. Okay. Now, here's what I will do. Here's what I will do. First, we will find the Cn. Okay. So if I write that fx, this fx then can be represented by c0 plus c1x minus a plus c2 x minus a squared plus c3 x minus a cubed and on. Everybody okay? Let me go to c4. X minus a to the power of 4 and so on and so forth. I want to find the coefficients C0, C1, C2, C3, and on based on the function. Okay, so first I will do this. From here, I will go to two directions. First, what is FA? When you replace x by a, what do you get?
C0 plus C1 times A minus A.
Yeah, so everything here will be 0. Right? Everything here will be 0. Is it right? When you replace x by a, only C0 survive. Okay? This makes sense? Maybe I'll write it down then so that you can see better. That's C0. Now, I will write it backward. Therefore, C0 later on will be replaced by FA. Agree? In other words, I can update my function. Let me go a bit to the right. I can update my function as fx equals to, I will copy paste this thing here. Put it here. No, that's not right. But I will replace the C0 by FA. Is it okay? Now, the second thing to do is I will find the derivative of that fx. F prime x will be, so pay attention to this derivative. F prime x will be, so I do two things, okay? I replace the function dx by a, that gives me the C0, and then I do the first derivative. When I do the first derivative, C0 disappears. I will end up with C1 plus 2C2 x minus a to the 1 plus 3C3 x minus a squared plus 4C4 x minus a to the 4th, so on and so forth. I assume you're following me in writing. Then I will repeat the cycle. So then I will replace that x now by a. So if I replace the x by a, I will get C1 plus 2C2a minus a plus 3C3a minus a squared plus 4C4 a minus a to cube. I'm sorry, not to the fourth, it's cube here. And on, which is equals to what?
C1.
Equals to C1. So at this point, I can update my C1, my coefficient for x minus a to the 1. That's equals to f prime a. Okay, so I will copy whatever I have here. Whatever I have here, I will copy these. Oh, I make a mistake here. Good thing I see it. My bad. It's supposed to be x here. This is supposed to be x. This is supposed to be x. This is supposed to be x. Early. Okay, because we know fx and we know c naught. Now I update my function. Let me continue here instead. So my fx now being updated to c0, which is fa, plus c1, which is f prime a times x minus a, plus c2 x minus a squared, plus c3 x minus a cubed, plus c4 x minus a to the 4th, and on. Now, I want you to see the advancement. Earlier, we know this as C naught. Now we have that value. And earlier, we know this is just C1. Now we know that's f prime a. Okay? Now, imagine if I do the next derivative, f double prime x. So if you do the derivative from here, from f prime x, so from this f prime x here, you do another derivative. Then you will get 2c2 plus 3 times 2c3 x minus a plus 4 times 3 c4 x minus a squared, and on. Now I will replace the x by a. Therefore, my C2 equals to f double prime a over 2. If I try to keep track, let me keep track of that here. If I try to keep track, my C0 is fa. My C1 is f prime a. My C2 is f double prime a over 2. Now imagine if I do another one derivative. Then I will get 3 times 2c3 plus 4 times 3 times 2c4 x minus a, and on. And if you replace that third derivative x by a, you will end up with 3 times 2c3. which implies C3 equals to the third derivative of A divided by 3 times 2. Then keep track next door. C3 is F third derivative of A over 3 times 2. I will do one more time. If you take a look on the fourth derivative, the fourth derivative of x, then you will get 4 times 3 times 2, C4, plus blah, blah, blah. Actually, the blah, blah, blah will be 5 times 4 times 3, C5 x minus a, plus 6 times 5 times 4, C6 x minus a squared, and on. For which, if you replace the x by a, you will get 4 times 3 times 2, C4, which implies the coefficient for x minus a to the 4 will be the fourth derivative at a over 4 times 3 times 2. Now, of course, you can keep on going, but I hope we see some pattern already. We can rewrite this as f, the fourth derivative of the function f a over 4 factorial. This is the third derivative of f a over 3 factorial. This is the second derivative f a over 2 factorial. This is the first derivative f a over 1 factorial. This is f a without derivative over 0 factorial, which is 1. So, our fx now can be represented by the C0 will be fa. The C1 is f prime a over 1 factorial of x minus a plus the second derivative of a over 2 factorial x minus a squared plus the third derivative at a over 3 factorial of x minus a cubed and on. Now, when I go on, let me write it in the general term. That will be the nth derivative at a over n factorial x minus a to the n plus dot dot dot, which I will write as the summation from n equals 0 to infinity, the nth derivative at a over n factorial x minus a to the n. Okay, I spent how many minutes with this? 15 minutes, I guess. This is what we call Taylor series. This is Taylor series about x equals to a. Okay, now Maclaurin series is the case when the a equals to 0. Maclaurin series is the special case of Taylor series. Where the centering is at 0. Okay, so basically Maclaurin series is fx equal to the summation and equals 0 to infinity. I replace the a by 0. I replace the a by 0. Okay, now one of the very well-known Maclaurin series is Maclaurin series for e to the x. Our textbook does this. Our textbook does this. Find Maclaurin series for fx equals to e to the x. And its radius of convergence. I will do radius of convergence later on. I will do radius of convergence later on. But let's find the Maclaurin series. The procedure seems to be long, huh? Okay, but basically we want to find, we need to find solution. We need to find the Cn, okay, which is known to be the nth derivative at 0 of the function over n factorial. Okay, but if that's the case, we basically need to find f and 0, the nth derivative at 0. Okay, now start. I will start from f0 equals to e to the 0, which is 1, right? Okay, now then how about that's fx equals to e to the x, right? So how about f prime x? That's still e to the x. So f prime 0, it's still e to the 0, it's still 1. And so on and so forth, right? The derivative of e to the x is always e to the x, such that we find out that the nth derivative at 0 for this function is always 1. Do you notice that this is now 1? Right? So the Maclaurin series will be e to the x is equal to the series from 0 to infinity of 1 over n factorial of x to the n. Which, if I expand it, it looks like when n equals to 0, that's 1 over 0 factorial plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus 1 over 3 factorial x to the cube, so on and so forth. Now 0 factorial is 1. And so on and so forth. Okay. Now, how about the radius of convergence? If we want to find radius of convergence, to find R, the radius of convergence, I'll apply ratio test. I apply ratio test, which is the next term, x to the n plus 1 over n plus 1 factorial times n factorial over x to the n, that is in absolute sign, that is equals to absolute of x over n plus 1, which goes to 0 as n goes to infinity. Right? Because this is 0 for every x, which is less than 1, so the radius of convergence is infinity. Which means this series, this series that we have earlier, here can approximate the value of e to the x for whatever x. For whatever x, this series can approximate that very, very well. Okay. Now, of course, the larger the x, the more terms we may need. Okay. The larger the x, the more terms we may need. But as long as you go far enough, eventually the series that you have on the right-hand side, will give you a good approximation for e to the x. Okay. At that time, you can decide how many decimal places you want it to be. Okay, then I can find how many terms I need to do it. Okay, now that's one very well-known one. Unfortunately, you have to memorize this though. Okay, you will see later on there are some series that you have to memorize. Maybe I'll list that for now. I'll list that first for now. The one that you have to memorize is 1 over 1 minus x equals to the series of x to the n from 0 to infinity. Okay, and then of course 1 over 1 plus x squared, that's the alternating series for x to the 2n. Then ln 1 plus x was represented by the series, alternating series is x to the n becomes x to the n plus 1 over n plus 1 from n equals to 0 to infinity. And another one, that's what we have from last section, tangent inverse x is the integral of that, the series from 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1. Memorize that, memorize that, memorize that. So just now we get one more things to our list. E to the x is the series from 0 to infinity of 1 over n factorial x to the n. Okay, I plan to do more though. I plan to do more, but let me cover one kind of question our textbook didn't do. Our textbook does not do. I actually look for that kind of question around. I don't find it at all. I look for that kind of question around. I don't find it at all. It's this question. It's this question. It's not in our textbook. Okay, so for example, let fx equals to 1 over 1 minus x. And then the question is find f the 10th derivative of the function at 0. Solution. Don't try to do it one by one. It's like the first derivative, second derivative, fourth derivative. No, please don't do that. Okay, please don't do that. Now we know that 1 over 1 minus x is representable by the series 0 to infinity of x to the n. Is it right? At the same time, we know that the Maclaurin series for this is f n 0 over n factorial x to the n. That's the Maclaurin series. Okay. From there, we see that the coefficient for the 10th term, the coefficient for the 10th term, the 10th term coefficient is 1 on the left-hand side. On the right-hand side is f 10th derivative of 0 over 10 factorial. Now we get the answer. So the 10th derivative of at 0 for this function is 10 factorial. Okay. And you can apply this for basically all the power series that you know the extension, okay? The Maclaurin series, okay? Now, I will do one more and I will continue on Wednesday, but I hope you read this section and you memorize the list you have on page 786. Page 786, there's a box there, table 1, memorize that. If you don't memorize it, at least put a, what you call that, the book partition, right? Okay, so that for the test, you can open that book quite fast. Okay, memorize this. Memorize this. Okay, the one I want to do next is find Maclaurin extension, Maclaurin series for y equals to sine x. Okay, so y equals to sine x, y0 equals to 0. Y prime is cosine x, y prime 0 is 1. Y double prime is negative sine x, so y double prime 0 is 0. Y triple prime is negative cosine x, while triple prime 0 is negative 1. And then you will see we go back. So if I write the pattern, I will get sine x is equal to 0 plus, supposed to be 0 over 0 factorial, plus 1 over 1 factorial x, plus 0 over 2 factorial x squared, minus 1 over 3 factorial x cubed, plus 0 over 4 factorial x to the 4, plus 1 over 5 factorial x to the 5th, and on. Okay. Which if I simplify, I get 1 over 1 factorial x minus 1 over 3 factorial x cubed, plus 1 over 5 factorial x to the 5th, minus 1 over 7 factorial x to the 7th, and on. In summation notation, that will be the series. It is an alternating series, right? Okay, I would just consider x cubed, x to the 5th, x to the 7th. That's x to the 2n plus 1 over 2n plus 1 factorial. I need you to memorize this. I need you to memorize this. Okay? Suppose I want to find out what is the 10th derivative of sine. So let fx equals to sine x. Find the value of the 100th derivative. Why not 100? At 0. So I look at the series. I look at the series here. Okay. Now, how about the 100 for x to the 100? What is the coefficient? Answer me this. What is the coefficient for x to the 100?
1.
Huh?
1 for x.
I don't think so.
For x.
For what n will this becomes x to the 100? For what n? When n equals to 50, that's x to the 101. When n equals to 49, that's x to the 99. Right? So the coefficient of x to
99
the,
over 2?
repeat again?
Is it 99 over 2?
But we don't have such n though. N has to be an integer, right?
Yeah.
Okay, so the coefficient of x to the 10th is 0. Right? Because if you extend this, you will get -1 to the 49 x to the 99 over 99 factorial, and then plus -1 to the 50 x to the 101. You happen to skip that x to the 100, right? Okay, so 0 equals to f the 100 derivative at 0 over 100 factorial. So the 100 derivative at 0 is 0. Okay, I will stop here. What's your suggested homework for this? Suggested homework for this 11.10a. To find the Maclaurin series first, I would like you to do number 5, number 5 to number 9. Let's put it 5 to 9. Actually, if possible, go on with number 29 to number maybe number 29. Number 29 is find the extension of for the Maclaurin series of sine pi x. Yeah, basically you replace the x by pi x. You replace x by pi x. That's basically what happened. Okay, so we do substitution again. Now our what we will do is, of course, Monday we don't have class. We have class again on Wednesday. And then the Monday after that, we have test 4. Okay, I will try to do the following. Between today and Wednesday, I will try to record a lecture video for the later part of this 11.10. Okay, just in case you want to study during this long weekend. And then on Wednesday next week, I'll just do problems. Okay, that way then you can study some at home, and you can start studying from my old test already. Just avoid anything with Maclaurin and Taylor series thingy. Okay then, that's for today.